All right, well, welcome back. And here we're going to talk standard deviation. Now, you did talk standard deviation a little bit back in Math 9. So if you recall, with standard deviation, you talked about two kinds. You had theta x, which stands for the full population for a standard deviation. Or you have the Sx, which is for a sample. And the majority of the time you do have a sample, and that's what you're going to end up using, but we're going to be dealing with more this time around of the theta x there. So standard deviation, what that measures is how far from the mean that you are. So we talked about mean and median. We went over it last week. Those are what we call your measures of central tendencies. Again, those means and medians there. But when we start talking about dispersion, so how far apart the data is, that's when we start talking standard deviation. Another number that we like to look at too is your interquartile range, which if you remember from last time, that's your Q3 minus your Q1 there. So when you're dealing with dispersion, it really fluctuates. Sometimes you don't want to have a lot of dispersion, so you want to have a smaller standard deviation because you want to have your numbers closer together, whereas other times you want to show that there's a lot of dispersion or a lot of diversity, as they also like to say. So then you want to have a higher standard deviation. And again, it just depends on what situation you are dealing with. Now, you haven't seen this yet before. This is our standard deviation formula. So this is what the calculator is doing for you when it's calculating your standard deviation. So if you look at all these parts, we actually know these various parts here. This little funky E guy, we learned that during sequences. That's our summation symbol. So if you remember with summation, that simply means you're going to take each term and you're going to add them together. So this is saying you're going to add each term together and then multiply it by 1 over n. So n is just how many terms that we have here. So if you have 6 terms, it's 1/6 times your summation. So then what you're doing is you're taking your value and you're subtracting the mean from it. Remember that x with the bar over it, that is our mean. Because again, standard deviation is figuring out how far from the mean are you. So that's why you're taking the number and you're subtracting the mean from it. So you would actually square that value. And then you would add the next one squared to it, the next one squared to it, and the next one squared to it. Because sometimes what ends up happening is you get negative numbers. We don't want the negative versions of those numbers. We want them to be positive because negative tells us direction, and we don't care which direction we are in. We just care how far are we actually from that mean value there. So if we take a look here, exercise number 1, both of the following data sets have means of 5. So I wrote right here, mean of 5, mean of 5. So they're telling us both those data sets mean of 5. They want us to calculate the standard deviation of both data sets using the formula above and round your answers to the nearest tenth. So I'm taking my numbers and I'm going to plug everything in for here. So for data set 1, we have 1, 2, 3, 4. So my n here is a 4. So I'm going to plug that in for the ends of my equation. My mean is a 5, so that's going to go in there for the x bar, our mean value at there. So I'm going to grab another piece of paper here for a second. So this is what I'm able to fill out at this point in time for this first data set here. I got 1 over 4. Let me zoom in. That might make it a little easier for you. So we got 1 over 4. My summation is starting at 1. It's going to go up to 4 because I have 1, 2, 3, 4 values. So 1 to 4. I left it like this for right now. This is my generic formula, so I left it just like that. We're going to plug each term in. So how that would look is you would have 1/4 times. So I'm going to start my first number. My first number here is a 2. So if I plug in a 2 here, 2 minus 5 would be -3, and then it's going to be squared. plus my next number is a 4. So if I plug 4 here, 4 minus 5, it'd be negative 1 squared plus, plug in a 5. 5 minus 5 would be 0. 0 squared is just 0, so I'm going to leave that as a 0. And then my 9. So 9 minus 5 would give me a 4 squared. So I got to add those values up before I do it times my 1/4. So 3 squared is 9 plus 1 plus 0 plus 16. Add them all up times 1/4. Take the square root of it, and you would get 2.54. You'd get that decimal right there. So you'd get 2.5 when we round to the nearest 10. So the standard deviation for these numbers is a 2.5. So pause the video. Try using the formula on those next data points. Let's see what we can get. So the second one here, when I plug them in, square my values, add them, times 1/4, square root sign, we get a standard deviation of 0.07 on this one. So if we were to start trying to compare things, which that is the main point of our statistics, is to be able to take numbers and then compare them, what we would end up finding out here is this has more diversity in the numbers because my standard deviation is larger. This one over here would have less diversity in the numbers because the standard deviation is smaller. So what that's saying is these numbers are closer together than these numbers are going to end up being, which we can already see just by looking at those points before we actually got into it. But it's not always that simple to be able to just look at them and tell which ones are going to be closer together than the others. So this one, closer. These ones are going to be further apart. So in all practical applications, we assume the use of the graphing calculator to find the standard deviation of a data set. So in exercise 2, we are going to actually do that. Okay. So we got biologists studying the weights of brown trouts in upstate New York streams. As you can see, I'm telling you, they took a sample because there's no possible way that they could weigh every single trout in that stream that they are looking at. So they took a sample of only 15 of the trout. So we got 15 trout. Their weights that are accurate to the nearest hundredth of a pound are given here. So these are all of their weights. So they want us to figure out the mean and the standard deviation rounding to the nearest hundredth of a pound. So take a moment, type all of these numbers into your list, your L1, just like what we were doing last week, and do your 1var stats in order to figure out your mean and your standard deviation, which you should end up getting 1.92 and then 0.63. Okay. So now they want us to sort this information here. So the way you would do that is if you have all of your numbers typed in there, if you go to stat, they have a sort A. See if I can get this to show up. Sort A. So I'm going to select that. And that's going to sort my list from least to greatest. So then if I hit second and the number 1, it puts the L1 in there because that's where all my numbers are. So I want list 1. And then I hit enter. It's telling me it's wrong because I don't actually have numbers typed in because I didn't type them in. So let's go ahead. I'll put some of these numbers in here. So 4.5, 1.6, 1.53, 2.89, 2.85. I'm not going to put them all in there because I just want to show you this. So again, stat, choice 2, we want to sort. It's already got my list 1 in there for me. But again, second, and then the number 1 gets you that list 1 in there. And then hit enter, and it tells you it's done. So it has sorted my list in order from least to greatest. So if I go and I look back at it, it has, in fact, already resorted my numbers for me. So you never have to worry about sorting. The calculator will do that for you. So they want us to use our answers from part A, determine the percent of the trout that will fall within 1 standard deviation of the mean. So what that means is 1 standard deviation within the mean is It could go higher, so in which case it's going to be the mean plus 1 standard deviation, so trout that are weighing 2.55, or it could be 1 lower. So again, this is 1 higher. This one is 1 lower. So since it just says 1 standard deviation, they didn't tell you what they wanted higher or lower, so you have to do both. So unless they specifically say, you have to do both. So mean minus a standard deviation, mean plus standard deviation means we're looking at the trout that weigh 1.29 up to 2.55. So if you look through your list, you can count how many there are. 10 out of the 15 end up being that weight between 1.29 and 2.55. So that ends up being 66.7% of the trout are within 1 standard deviation of the mean. So we can finish that sentence off. Are within 1 standard deviation of the mean. Okay. So number 3 here, let me zoom back out a little bit, move this guy up. So they want to know which one has the smallest standard deviation. My little note here, as you can see, that means the numbers are the closest together. So again, smallest standard deviation means the numbers are the most similar. If you have, a little extra tidbit here, if you have a standard deviation of 0, that means the numbers are exactly the same. Numbers are exactly the same. So again, standard deviation of 0 means it's all the same. So if you look at this, with your 4 choices, the ones that are closer together is choice 4. So that one's going to have the smallest standard deviation of your 4 options there, and you don't even need to type that into your calculator. So again, population, sample, 2 different standard deviations when your calculators, when you do your 1-bar stats, they both show up. So, we got a car company trying to test fuel efficiency for, you probably already saw that, but trying to test fuel efficiency in miles per gallon of their latest hybrids vehicles. They drive a sample of 50 of these vehicles and determine their fuel efficiency. So L1, L2, we have a frequency list here. So calculate your mean and your standard deviation to the nearest hundredth. So again, when you do your 1-var stats, you got to have L1 and then you got to have L2 listed in there, since you do have a frequency list this time in this table. So go ahead, type those numbers in. I'm even going to sit here and retype them in. 37, 38, 39, 40, 41, 42, 6, 18, 15, 1. To get your L2 in there, just hit your second and then the number 2. And so there we go. So we do have a sample here. So actually, my standard deviation is off a little bit. I want to use the SX there. So 1.09. So in this case, being off by 100th is not going to be that big of a deal. But when you're dealing with other problems, it would be. So they want to know, based on A, how many cars in this sample had a fuel efficiency more than 1 standard deviation below the mean. So we're just going below the mean this time. We're not going above. They want to know how many cars in the sample had a fuel efficiency more than 1 standard deviation below the mean. So correct that to my 1.09. So that gives me 38.39. So if we count them up, excuse all my pens, they were below the 1 standard deviation, which would be the 38.39. They're below that. And so are these ones. So there's a total of 8 cars that are more than 1 standard deviation below, because this value right here is 1 standard deviation below. So 8 of them are even further below that. So then they want to, the government will allow only the company to advertise a fuel efficiency for a vehicle that is at most 2 standard deviations above the mean. Can this car company claim this car gets 42 miles per gallon? Explain. So again, let me fix my little mistake there. So if we do our mean plus 2 standard deviations above the mean, 41.66. So this is 2 standard deviations above the mean. Do they have a car that gets more than that? They sure do. They did have one that got more than 41.66 miles per gallon. So that, yes, they can claim it because it did actually happen for one of their vehicles. And then last one, in which of the following would it be appropriate to use the entire population instead of a sample? Now for this, sometimes a sample is more appropriate because you can't possibly survey or weigh or measure the entire population. So for example, if we go back to the trout problem, we wouldn't have done an entire population there because there's no way for you to have caught and actually weighed the entire population of trout that were in there. So that one had to be a sample. So this one, they want to know when would it be more appropriate for an entire population. So determining the average weight of New Yorkers. You're not going to be able to weigh every single New Yorker. Determining the average time spent on cell phones by American teenagers. You're not going to be able to survey every single American teenager. Determining the average quiz grade for a given Algebra 2 class. And it ends up being that one because that's a smaller group that you're looking at. You're just looking at one class. So it's going to have 25 to maximum 30 students. So it is actually possible to do that entire population. Whereas the other ones, this one looking at Atlantic salmon, you're not going to be able to look at every single salmon out there. So it's not going to be possible for that either.